James Clerk Maxwell's equations for electromagnetism rely on a rigid geometric separation. In classical theory, the electric field acts as a tangent vector, while the magnetic field acts as a surface normal. They appear in the same equations, yet are described as separate physical entities. In the realm of optics, we find Malus's law. It predicts exactly how much light survives a polarizing filter based on a squared sine equation. Intensity equals initial intensity times the sine squared of the angle. Moving into the abstractions of analytic number theory, we encounter Catalan's constant. Represented by the letter G, this number, 0.915, serves as a fixed point in the study of prime number distributions. Standard theory treats these three phenomena as independent. They occupy different disciplines and operate at different scales, seemingly sharing no common structural root. However, the Gaussian prime physics framework suggests that the electric and magnetic fields, the polarization rules of Malus, and the convergence of Catalan's constant are the exact same mathematical object viewed through three different lenses. This unified root is an Euler product operating on a mod 30 coprime lattice. It defines a T1 Möbius toroid, a surface carrying 8 specific lanes that represent the surviving integer winding paths. This topology is non-orientable. Because of a half-twist at the boundary, a path must complete 2 full revolutions, 720 degrees, to return to its starting state. This geometry builds upon a single postulate. Time is a one-dimensional string with tension equal to the speed of light. When this string deflects, the interior of that curve generates the 3 dimensions of space. Mass, in this view, is the curvature resulting from that deflection. By tracking how integer winding paths traverse this specific half-twist boundary, we can derive the governing laws of both physics and mathematics. On a standard torus, opposite waves interfere to produce a cosine pattern. A Möbius half-twist forces the returning wave to invert, shifting to an antisymmetric sine wave. Squaring this amplitude gives physical intensity, a projection weight equal to the sine squared of the winding angle. The physics of a half-twist boundary generates the identical sine squared pattern used in optical polarimetry. This provides a topological mechanism for Malus's law, originating at the subatomic scale. Projecting this squared sine across the 8 coprime residues causes the wave to decompose into classical Ramanujan sums. Ramanujan sums are the foundation of discrete Fourier structures, the same arithmetic objects used to analyze signals and complex waveforms. Macroscopic polarization is the bulk manifestation of this exact phase interference occurring at the toroid boundary. The geometric split of the electromagnetic field becomes visible if we examine the winding phase before it is squared, the raw sine amplitude. The Möbius seam divides the lanes into forward C1 and return C2 windings. Squaring the amplitude removes this sign distinction, creating a tangent scalar, the electric field. Leaving it unsquared preserves the antisymmetric split, generating a normal-handed vector, the magnetic field. This even and odd Fourier split maps to the fundamental properties of electromagnetism, where E acts as a scalar tangent and B acts as a handed normal. The electric and magnetic fields are fundamentally merely the symmetric and antisymmetric halves of a single winding phase. We find the same geometric split within the infinite sequence of prime numbers that build these residue lanes. A Dirichlet character, chi-4, categorizes every prime based on its chirality. Primes that are 1 mod 4 belong to the C1 lane, while 3 mod 4 primes belong to C2. These prime categories filter directly into the 2 sides of the physical Möbius seam. An Euler product formula captures the sorting process. As we account for more primes, the product converges to a fixed point, Catalan's constant. Catalan's constant acts as the numerical witness of this balance. It measures the stability of the convergence between the 2 topological lanes. The physical balance of the E and B fields and the numeric balance of prime factors are determined by the same Euler product fixed point. The C1 and C2 lane balance determines the behavior of the Mertens function, a running sum of the Möbius function that tracks prime factor parity. Because the prime factors are governed by the same Euler product, their distribution follows the chirality of the lanes. A proven identity pairs every C1 prime with a C2 mirror partner, forcing the Mertens function's chaotic oscillations to perfectly cancel out. This structural pairing traps the sum, ensuring it never grows faster than the square root of the number of terms. Proving this boundary is equivalent to proving the Riemann hypothesis. The placement of the zeta function zeros depends entirely on this cancellation remaining stable. The Riemann hypothesis represents a statement that the Möbius-Euler product maintains an exact topological balance. Optical polarization, electromagnetism, and the distribution of prime numbers are simply the expressions of a single underlying geometry. The electric field split, Malus's polarization rules, and the Riemann hypothesis constitute the same geometric statement. The framework reveals physics and number theory as the exact same geometric machine, running at entirely different scales.